I'm Zack. I'm a student from University of California, San Diego, and I've been researching here at in Taiwan for the past month at DSL under the leadership of Sun Kang right there. So I start? Yeah. Okay. So over this past month, as part of my research, I've been designing a DSL in Scala for a ubiquitous computing environment. And over the course of this project, I've learned a lot about the Scala language and DSL design that I'd like to share with you today. And so first I'm going to talk on some top-level stuff like theory, then talk about how you can use Scala to develop a good DSL, and then run through a brief overview of making a mini DSL using Scala. So what is a DSL? If you look on like Wikipedia, you'll probably see a definition like this, something like, oh, a DSL is tailored for a specific domain. And what this really means is that the semantics of your language should model the semantics of your domain. And the DSL tries to do one thing and one thing well. And this is in contrast to a general programming language like C++ or Java, where it can handle any sort of domain that you throw at it. And DSLs come in many different types and sizes. They have different scopes. And a lot of the bigger ones you've heard of are probably like SQL for databases, MATLAB for mathematical processing, LaTeX for typesetting, but really there are like thousands of DSLs used at a much lower level. And when it comes to designing DSLs, there are really two main types. You have embedded DSLs and standalone DSLs. And in a standalone DSL, the DSL is a full language in itself. So HTML is a big example of this. Most of the DSLs that everyone uses daily are examples of these so-called standalone DSLs. And then the other type, we have these so-called embedded DSLs. And these are built on top of an existing language and often imported as in like a library. So an example of this would be like Scala tests, which is a library for writing specification tests in Scala. And to use Scala tests, you need to import this library, and of course, Scala test itself is written in the Scala programming language. So now, let's say you want to write a DSL for your project. At first, you'll probably think, oh, I'll just do a standalone DSL, because I can define my own syntax and semantics. You have ultimate freedom to choose anything. But this freedom comes at a cost. And the cost is designing syntax and semantics are really hard. I mean, at the very basic level, you'll need to have a lexer and a parser, and then maybe an interpreter and a compiler. And if your DSL is going to have any sort of programming functionality and you need to handle like making a type system and doing function call semantics, you're going to find yourself reinventing the wheel. And you'll never be able to compete technically with a general purpose programming language in this aspect. And additionally, if you have your own custom syntax and semantics, other people may not be so willing to use your DSL. And a good example of this is a language like Vim script. So there's a lot of Vim coders out there, but not a lot of Vim developers. And the reason for this is if you want to write a Vim plugin, you got to learn this weird language, and it's not a lot of fun. So that leads us on to the other type of DSL, which I'll talk about today, this so-called embedded DSL. And writing an embedded DSL is really easy because the parent language has done all of the hard work for you. You can start writing your embedded DSL with just a few lines of code. Now, of course, there are limitations with this approach too. That is, whatever syntax that your parent language uses, you have to use too. That is, you can't like overwrite keywords. You probably can't create new keywords in your language. And then you're going to be limited technically by whatever technical limitations that your parent language has. So if your parent language does not support static typing, your DSL can probably not be statically typed. And as I'll show you guys today, this choice of a parent language is very important, and Scala makes a good candidate for writing an embedded DSL. And now, embedded DSLs are further embedded into two different categories, deep and shallow embedded. In a shallow embedded DSL, your DSL instructions get translated into one or more instructions in your parent programming language, and it's kind of more of like a not very sophisticated, not very much of an abstraction. And the other way of designing a DSL is a so-called deep embedded DSL. And in this DSL, you separate the syntax of your language from your semantics. That is, your DSL instructions themselves are creating some sort of like intermediate data structure, similar to an AST. And this is a little bit more work than creating a shallow embedded DSL, but your resulting DSL becomes a lot more powerful because you can perform AST manipulations and separate your syntax and semantics. Okay, so now why do you want to create a DSL in the first place? A lot of people think when you have an embedded DSL, you're really just kind of adding a layer of like syntactic sugar, and you're not really helping solve the problem in a fundamental way. But it's my kind of belief that actually in most software projects, doing a good DSL is the most important part. And the reason is a lot of problems in computer science kind of look like this. You have some domain that you want to solve a problem in, such as physics. And the first thing you'll want to do is write a physics equation to solve your problem. Now, of course, this isn't enough. You need a computer to do your thing, so you take your physics equation and convert it into C++. Then, after a lot of hard work, you compile your code, run it, get the answer, and your solution is in your domain. Now, most of the work that you have to do kind of happens in this step right here. And this is exactly where the DSL comes in. The better your domain language is, the closer the language of your domain is to the language of your code. And this reduces the amount of work of this translation process by a large amount. And in theory, if you had some perfectly awesome DSL that modeled your domain perfectly, really this structure right here would just reduce to this, where in a perfect world you just describe what problem you had in the domain, and your awesome DSL, which understands the domain language, gives you a solution right away. Of course, this is kind of impossible, but it would be a nice goal to realize. So what makes a good DSL? And it will depend a lot on exactly what you're trying to accomplish, but I think the most important aspect is that the semantics of your DSL match the semantics of the domain. That is, if you have a statement that is not in your domain, like statements outside of your domain, you should be unable to represent them in your DSL. You should only be able to represent valid statements in your domain. And the best way to tell that you've really done this is if someone who knows nothing about programming but knows everything about the domain can look at your code and understand exactly what it's doing. It should be just intuitively obvious when you look at your code exactly what it means in terms of the domain. And along with this, you would hope that your DSL is very expressive in the domain. So if you're designing like a typesetting language, you should make it really easy to talk about how to lay out documents on a page. Like your grammar and syntax you use should make it really obvious. And if you're developing a physics engine, every sort of like term in like your physics should be a first-class citizen of your DSL. And likewise, outside of the domain, your DSL should not try to do anything. Like there's a reason why typesetting languages aren't Turing complete, and you don't want to introduce complexity where you don't need to. And if you can do this, you'll get a lot cleaner code with less boilerplate, easier to understand, and you'll have fewer bugs and a faster development cycle in the long run. So now, when should you make a DSL? And I would say almost always, and I'll get into why just right now. When people talk about type systems, like one of the first things they say is like, you know, if you have a good type system, whole classes of errors will just no longer occur. Like you're not going to get any runtime type errors in your statically typed language. And this is touted as a benefit. And likewise, like functional programming, if you code in a functional language, there's a whole class of errors that you're just not going to encounter in your programs. And likewise, if you really model your domain well with this domain language, there will be another class of errors that you aren't going to get. And the class of errors that I think are the most really important to try to get not occur. And these are errors where you're making statements that are legal in your code, but illegal in the domain. If your domain language is good, if it's illegal in the domain, it should be equally illegal in your DSL. If it's illegal in the domain, it should be a compiler error in your DSL. And you can accomplish this if your language has types or other facilities for raising compile time errors. So this is good, but maybe you might think, oh, well, just designing a DSL is hard, and I don't know how to do it, it's just too much work. But for this, I would say, is also kind of a bad way of thinking, because on any sort of medium or large size project, you're going to be building a DSL anyways. Like, as you code your project, certain patterns start to emerge, and certain like opportunities for abstraction arise. And you will want to take these, of course. But the problem is, if you're just casually taking these abstractions, you'll be building up this kind of accidental DSL. And what you don't want to happen is being halfway through your project and suddenly realize that the domain you've modeled is not the actual domain you wanted to model. And then you have to refactor all your code. since you're going to be designing a DSL anyways, you're going to be designing all these abstractions in the first place, it's just better to get them out of the way up front so you don't have this crisis halfway through your code base. Okay, so enough with the theoretical stuff. Now I'm going to talk about why Scala itself is a pretty good language for DSL design. So the first is the syntax of Scala is really, really nice. You can tell that like this was a really key design consideration by the developers. When most people start learning Scala coming from Java, they will write Scala code that looks exactly like Java code. And I think a lot of people do this with every language. Like people who start learning Python will try to write like Java Python or things like that. But as you learn more of the Scala language and learn about tuples and anonymous functions and pattern matching, your code looks more and more concise, and the Scala compiler will happily compile that as well. I mean, Scala itself is known as a so-called scalable language for writing like from small scripts to giant project, and the syntax is sort of scalable in a sense as well. And when it comes to designing a DSL, you have a lot of freedom in a syntactic sense. Plus, you can define infix, postfix, and prefix operators in Scala, as well as define symbolic operators such as plus, minus, greater than, etc. Another cool feature of Scala that I don't know if other languages have is this user-defined implicit conversions. So in Scala, what you can do is you can have a conversion from one type to another that you define in your code, and this conversion happens at compile time, not at runtime. And it's a little abstract, but I'll go into a more detailed example later. And Scala is functional, which, I mean, you guys all know how that's good, and it's type safe, which means that you can model objects in your domains using the type system of Scala and get all the benefits of that. And finally, Scala also supports macros, which are a really good tool for designing abstract DSLs. So to start with some of the syntactic sugar in the language, we'll just start at the very basics. In Scala, you don't need semicolons, and you can replace these periods and parentheses in a lot of cases. So in Scala, this expression right here and this expression right here semantically are the same. But as you can probably tell, this is kind of a little more obvious. It reads just like an English sentence. Result should be 3. Everyone knows like what's that saying about result. So to show a little example of how Scala can be used really expressively in this way, let's see if we can kind of pretend to add a keyword in Scala. Not actually add a keyword, but just create a function like this unless one. And the way unless works, it's just like if, but opposite. It takes some condition and a body. And if the condition is false, the body is evaluated. And this is how it's defined, and this is how we would call it right here. And so unless takes 2 parameters. And the first parameter we can put in like parens because that's just how an if statement would look. And then the second parameter, since it's like a function, we can put it in curly braces. And since Scala allows us this really nice syntax for defining anonymous functions, this right here looks almost as it would if it was a real first level Scala keyword. Except the only difference is that in the body we're passing a function, not an expression. And so along this lines, because we can remove these dots and parens and so forth, you can take any method with one parameter and use it as an infix operator. So when you type something like a plus b, what actually happens is in the Scala language it gets de-sugared into this a dot plus b. And additionally, we can abuse these symbolic operators like plus and less than. So suppose we're writing some DSL, and in the DSL we have this concept of an expression. And we'll have 2 types of expressions, integer expressions and a way to say less than expression. And calling this less than constructor is kind of ugly. What we really want to do is just say like 1 less than 2 and have that become an expression. And in Scala we can do something like that. So we'll define the less than operator on this int expression. And it does not return a boolean like you would expect normally. Actually, it can return a new expression. So when you write something like this, it evaluates to this. But from the writing perspective, this is a lot more obvious what it means. And additionally, we can define postfix and prefix operators in Scala. So let's say we wanted to recreate the Boolean like semantics, create our own Boolean class. And we want to talk about how we can invert the value. So we'll define some like trait here, which is like an abstract base class, and define some syntactics. Like inverse as a postfix operator, or unary bang as a prefix. Then define the concrete implementations. And now here we can say like print line not true, get false, print false inverse, and get true. Okay, so now implicit conversions are best sort of explained by just an example, showing like the motivation behind it. So let's say we have some DSL where we care just about apples, and we don't want to create apples like this because it kind of looks ugly. We don't really know what we're talking about. Really, what we want to say is just 10 apples. Like we want to write this. No one is confused about what this means. But in a language like C++ or Java, you really have no way of doing it. Integers don't have an apples class, and you don't want to do something crazy like Ruby-style monkey patching or extending the integer class. So what you can do is you can define an implicit conversion from int to appleInt. And what this conversion says is, anytime I see an int, I can convert it into an appleInt if I want to for some whatever reason. So when the compiler encounters this expression, it sees 10, finds that it does a type check in this context, looks for an implicit conversion, and finds one in appleInt. So what happens at compile time is that this 10 gets replaced with this appleInt object. And what's important to note here is that this conversion is happening at compile time, not at runtime. So this is not going to have any sort of runtime consequence in your program. It's not going to reduce your type safety, and it's definitely not going to cause any runtime type error. And this implicit conversion is the basis of this pattern in Scala called the pimp my library pattern, where you can just take anything that anyone's ever wrote and sort of extend it in this way by using these implicit conversions. And so now we can kind of see how all these features combined allow us to talk really naturally about things. And in many Scala libraries, this is exploited. So this, in the Scala duration library, we can talk about time really naturally, like 5 milliseconds. We can multiply time durations by integers or add times together. And it's very obvious what we're talking about here. And additionally, we can define like ranges really easily just by saying things like 1 to 10, giving us a range from 1 to 10. All right. So the next thing I would like to talk about is macros. And Scala macros are much better than like C macros. First of all, the language you write macros in is Scala itself. Scala macros are Scala code that writes Scala code. That is, your macro program is a separate program that must compile in Scala. And not only this, but the Scala macros don't operate on text strings, but rather they operate on expressions themselves. So your macro takes one or more expressions, which is just like nodes in the AST, and returns as output another AST node. And all of these nodes in the syntax tree are typed. So your macro is guaranteed not to cause certain types of typing errors. And macros are still an experimental feature in Scala, and they're now currently split into 2 different types. We have so-called black box macros, and these are safe macros because they cannot introduce new types. And you can type check your program before doing macro expansion. And then there's this more experimental type called white box macros, where your macros can actually introduce new types, and your types can be used later on in the program. So today I'll talk a little bit about how to use some of these black box macros. So going back, to start with a very simple macro, we can go back to this unless method that we talked about earlier. The thing that was kind of bad about unless was that it didn't take expressions as, like, it took a function as a parameter. You couldn't just put in whatever block of code you want. So we can make a little bit better version of it by using a macro. And you call a macro the same way you call a normal Scala function. So your macro has 2 parts. The part where you call from your main code and the part that generates code. And so here you can tell, okay, it's just takes a boolean, takes some sort of expression, and returns unit, which means returns nothing. Because if the condition is true, then it just has no effect. And it causes the expansion of this macro. And you'll notice here that this macro has the same shape as this function up above. But the difference is that instead of taking values, it actually takes the expressions themselves. So it does not take a boolean. It takes an expression that evaluates to a boolean in this context. It does not take any value. It just takes an expression that evaluates to any value. But the most important thing to notice is the return value. It's returning an if statement. that means your macro must guarantee that so long as you put in this, you're going to get an if statement, no matter what you evaluated. And so this is what the body of the macro looks like. And you might think I've just like tricked you guys, and actually this is just a piece of text. But actually this is a Scala quasi-quote. And what's happening behind the scenes is this gets turned into a constructor for an AST. It gets turned into a constructor for an AST again. So it's a little bit of magic, but if I were to modify this and turn this into like a while statement instead, the macro itself would not compile. Even if I never expanded it, it just would say, no, the output was a while, I need an if, it wouldn't compile. So obviously, from this example, you can kind of see how this would eliminate a lot of the problems that you constantly encounter in like C macros. And calling a macro from Scala is very easy. It actually looks just like calling a normal function. And what happens is, during macro expansion, this call gets removed and gets replaced with this code right here. And as you can see, the way we implement it unless is just negate the condition, fill in the body.
So now, can you explain that context?
Oh, yeah. The context is the compilation context, like where the expression was found in the code. So, like, your expression that evaluates to a Boolean could just be a function call or a value. It does not need to be a literal Boolean expression. So, as for Scala, we can use this macro system to have custom compile time errors because your macros can generate exceptions. And if your macro generates an exception, that will cause a compile time error in your code. The runtime of your macro is the compile time of your, the runtime of your macro, if you throw an exception there, it gets thrown at the compile time of your code. So let's say we wanted to create a class for a string with no spaces. One of the challenges with this is how you would define a constructor for a string like this. If you didn't have macros, really the best thing you could do is probably create a string constructor and then evaluate the string at runtime, and if it has a space, you throw a runtime error. But since we have macros, we can use macros as a way to throw a compile time error in this case. So we'll define this method here called fromString that takes a string and returns a non-space string. And one of the things to notice about this method is that it's an implicit method. So we can do these implicit conversions at compile time, and macro expansions also happen at compile time. So it's a little complicated, but you can also have an implicit conversion that generates a macro expansion. And what this means in practice is we never actually need to create a non-space string implicitly in our code. We just say where we need a non-space string, and the compiler will generate one for us automatically. And this is how we would generate the code right here. You can see that this make ns string has the same signature as this from string, except it's taking an expression of a string instead of a string. And then we need to match this expression. Now notice here we're only matching against string literals. So lots of expressions could evaluate into strings, like values could evaluate into strings, function calls could evaluate into strings. But for the purposes of our macro, we're kind of limited just to doing literal string expressions because we can't know what the result of a function call is going to be at compile time. And so the way this works here is we just get the content of the string literal, check it for a space. If it has a space, we'll throw an exception. And remember, this is the runtime of the macro, which is the compile time of your main program, so this exception occurs at compile time. And suppose it does not have a space, then we can just insert the constructor in its place. And here's an example of how we could use this. So we'll have some method here, like print ns string, that takes a non-space string as a parameter and just prints it out. And then we'll have our main function here. And when the compiler gets to this point, it's fine. This ABC string has no spaces in it. And the macro runs, and ABC gets replaced with the constructor for non-space string. But at this point, it finds a space, and the whole thing crashes. And the nice thing about this, the way it crashes, is it tells us where it happens in our code, where it happens in the macro code, and importantly, we can put whatever exception we want. So the reason I bring up this example is not to say that you should be creating these kind of types in your code, but more that you have another mechanism for causing compile time errors. If you can't make your type system figure out all the illegal statements in the domain, you can use macros as kind of another way to cause these exceptions. So now that we've gone over some of this basic stuff, I'll show a quick example of how we could build a deeply embedded DSL in the Scala language. So let's say we want to create something for rules, and we have a condition, which is kind of like a Boolean, actions, which are kind of like functions, and rules, which are kind of like if statements. So remember, this is a deep embedded DSL. So we'll need to define the semantics and the syntax separately. So at this point, we'll just kind of define the syntax. And remember, the syntax in our, like these DSL instructions, will just create a sort of intermediate data structure. So here we have this condition class, this trait attribute base class. And we say, okay, on any condition, we can perform these three operations. We can OR them, AND them, or invert them by putting a bang in front of it. And then we'll define these concrete instantiations. So these OR, AND, and NOT should be fairly similar. They're just like the normal Boolean concepts. And what you should note here is that in the AST that we end up generating, these will always be at internal node positions because they depend on other conditions. And now here we have these three ones that have meaning inside themselves. Like a dependent condition. The only one that's really different than, probably surprising, is this dependent condition, which is something that's a function that returns a Boolean. And these will always be in the leaf node position. So now, remember, we haven't really defined what any of these mean. We've only defined how you can put them together to make this sort of structure. So at this point, we can make statements like here below, say true and not false, or false or true. And what we generate is a structure that looks like this. So the next step is to define a way to evaluate these conditions. And to do that, we define some eval function that takes a condition in and returns a Boolean out. And the evaluation is very similar. Should be very obvious because this is not a very really abstract concept. We just, to AND two things, we evaluate them both and use Boolean AND, or not, do not. For the dependent condition, we just evaluate the function. And then true becomes true and false becomes false. So now on to actions. In our code, we have two different types of actions. We'll have an action that just is a wrapper around a function, and then an action that represents doing one action and then doing another. And we'll say for any action, we can define this and then method on it that allows you to combine method actions together. So you can say like action 1 and then action 2 and then action 3. And to make writing code in our DSL a little bit easier, we can create a wrapper, this implicit definition to write these wrapper actions that take any function and turn it into an action. And you can do this because Scala is a functional language. A function is just another type of object, so there's no reason we can't take an implicit conversion for it. So let's say we wanted to write hello world in a really stupid way. We could call say hello and then say world. And what happens here is say hello gets turned implicitly into this function action, and then you call the and then method on it, pass in a function as a parameter, which gets implicitly converted into a function action. And then the result is we get this function. And the evaluation semantics for actions are very, very simple. Like if it's two actions, you evaluate the first and then the second. And if it's just wrapping a function, you just call the function. And here's a good place to notice that because we've separated the syntax and semantics, if we wanted to change the behavior of our DSL by maybe running these simultaneously on each in their own thread, we could do that without changing any of the syntax of the language. So finally, we'll get onto the rule class. And the rule is a little more tricky. Here in this trait, we just sort of define the contract that our rules need to abide by. So every rule has to have a condition. Every rule needs an action. And maybe we can have an optional else action as well. So we'll define two different types of rules. One that's just like an if-then rule, and the other type of rule that has like an if-then-else. And you'll notice for the if rule, we'll have an otherwise method that allows us to put an else action and get an if-else rule in return. And of course, our if-else rule will not have this otherwise method because it already has some else action. And evaluating a rule is very simple now that we know how to evaluate conditions and actions. You simply evaluate the condition. If the condition is true, you evaluate the action. And if the condition is false, you evaluate the else action if it exists. And to kind of finish it up, we'll define two top-level methods for creating rules. Because calling this if rule construction looks a little bit ugly, we can just say when condition action create an if rule, and then we can also add this unless operator again that has the same sort of structure, except it only happens if the condition is false. And at this point, we are now able to write and evaluate statements that look like this. And just to break it down a bit, so we're calling one with two parameters. True and false is just a condition in our language, and this is a function. And remember, we can apply this implicit conversion, and this becomes a function action. So this, when true and false, currently won't see this, becomes an if rule. And then that if rule, we can evaluate the otherwise method on it, pass a function in, which gets implicitly converted into a function action, and then our result is an if else rule. So finally, we can evaluate this statement. And how this evaluates is, well, true and false becomes false. So we do this, we'll see this method. All right, so that about wraps it up. Thank you guys for listening. Do you have any questions?
Go back to the say hello world example. And what does the underscore mean?
Oh, yeah. So in Scala, if you have a method that takes no parameters, you can call it without parentheses. So the problem with that is if you want to return the function itself, you need to put an underscore to indicate that. So it's a little bit of a weird thing about Scala syntax.
So if there is no underscore, we probably
it would say, if you didn't put an underscore here, it would evaluate hello world, and you get like a unit, void, and then say, oh, void has no method and then. Yeah, you get a type error. Actually, the original version, earlier versions of Scala behaved differently, where you could just say hello and then say world. But then people started getting the other type of error, so they switched the semantics a bit.
I'm still confused about the context. So can we see that again? So in any program code with the context. So now C is the context, and condition. The type of condition used is C.
C
so does the C refer to the previous C?
Yes.
So
yeah, I actually don't know too much about how the macros work, but my understanding is that you can have in Scala you can have a kind of dependent typing, because your types can depend on C here is an object, and this is a type that's dependent on this object. So don't quote me on this for sure, but what I'm pretty certain this means is that it's an expression that evaluates to a Boolean in this certain context. But I'm not.
So it is expression of method of C, or
no, expression is a type. So you can have in Scala you can write an object, and the object can nest a type inside it. So yeah, this is definitely a type. So Scala does support this sort of dependent typing by having any sort of object can have types inside it.
I wanted a C universe.
This I'm not so sure. The reason it's included here is because to get the quasi-quote operator, you need to import the context, because which I think is because this expression here could mean different things in different contexts, of course. Thank you.
Thank you.